Ever wondered how scientists turn messy data into reliable answers? Think of it like tuning a radio. Sometimes you need more than a basic knob. You need precise adjustments to get the clearest signal. Today, we're diving into a statistical powerhouse called the one-step estimator, a tool that fine-tunes estimates with mathematical precision. Let's break it down. Let's start with a simple problem, estimating the average height of a group. You take a sample, calculate the mean, and that's your guess. But what if the sample is small, skewed, or full of outliers? That's where Taylor expansions come in. Remember those from calculus. They're like a mathematical shortcut to approximate complex functions. In statistics, we use them to model how estimates change when data shifts slightly. Imagine a curve representing data distribution. A Taylor expansion lets us guess its shape with a polynomial, simplifying the math. Now here's where the one-step estimator shines. Picture this: you start with a rough estimate, like a first draft of a story. Then you apply a single, targeted correction using the score function, a mathematical tool that tells you exactly how to adjust your estimate for maximum accuracy. It's like editing a manuscript once, but with equations instead of red ink. This correction is derived from the derivative of the model's criterion function, a measure of how well the model fits the data. But why does this matter? In real-world scenarios, like training AI models or analyzing medical data, estimates can be off if the data is noisy or limited. The one-step estimator balances bias, systematic errors, and variance, random fluctuations, acting as a Goldilocks zone, not too much correction, not too little, but just right. It's the statistical equivalent of calibrating a sensor to filter out static. Here's the kicker: this method isn't just for simple averages. It adapts to complex data shapes, like skewed distributions or outliers. By incorporating higher-order terms from Taylor expansions, it accounts for lopsidedness in data, making estimates more robust. Think of it as adding extra layers to a radio's antenna to catch signals that were previously lost. Imagine a self-driving car's sensors misreading a rainy street. The one-step estimator could help the AI adjust its predictions on the fly, avoiding errors that could lead to accidents. Or in medicine, it could refine a model's diagnosis when faced with rare conditions not seen in training data. The math is complex, but the goal is simple: make estimates smarter, faster, and more reliable. So what's the takeaway? The one-step estimator is a prime example of how statistical thinking turns raw data into actionable insights. It's not just about numbers, it's about adapting, refining, and getting closer to the truth. If you're curious about how these tools shape the AI and tech we use every day, hit subscribe. And next time you hear about statistical models, remember, they're not just equations, they're the quiet heroes behind every smart guess. Thanks for watching, and stay curious. Like this video if you want more deep dives into the math behind technology, and don't forget to subscribe for future episodes.